Okay, I think I finally worked out the technical issues, so now this should be live. So, I'm Ryan, as you may already know, and I'm going to be trying to do some coding today, trying to model a supernova. Now, as I'm going about my business, please do leave comments in the chat, and I'll try my best to answer them as we go. There's a bit of a lag between me talking and things coming up in chat, or me talking now and actually things going through. So there may be a bit of disconnect between what I'm saying and what you're asking. So hopefully that's not too bad. So the thing that we're going to be doing today is try and replicate these papers, or at least try and get close to replicating them. So this paper here, which is a paper by my collaborators, some people I work with, shock breakout and early light curve of type 2p supernovae observed with Kepler. Now the Kepler part we're not really too worried about. It's more this idea that we can try and simulate a supernova and get some of its physical properties. In particular, the properties we're wanting to get are the radius that you can see here. They have some estimate for the radius, and the mass. And the mass isn't so obvious here because I think the fitting for the mass isn't so great. But with these things we can say some interesting things about how the supernova actually occurred, and that is useful for trying to understand how stars blow up in the first place. Now these models that we'll be using might not necessarily be the best models or even good models. There is some debate going around that suggests that perhaps these models don't really represent the true complexity of nature, and that is certainly true. They're pretty simplistic models, but they will at least give us perhaps a first pass at understanding the supernova that's happening. So let's just quickly look at what this will be doing. So I'll jump through some of these figures. This one is the one I want. So they have two different supernova light curves here. Now a light curve is just the brightness of something measured over time. And you can see that there's not much happening, and then all of a sudden it gets brighter. So these red points are the points that this Kepler Space Telescope observed. And this green line here is the model that they fit. So it's not perfectly fit, and there may be other reasons as to why this isn't perfect. But the reason in this paper is that they say this supernova has some extra stuff surrounding it, so it's not particularly well explained by this model. But before we get into how all of this stuff works, let's do some explaining and some scribbling, because scribbling is always useful. So what you're seeing there is, or saw there, was the light curve. So it's pretty much something like this. You have the brightness up the y-axis, and then you just have time along the x-axis. Now, as I do this, you'll get to see my terrible handwriting, but hopefully you'll be able to read it. So usually, if you measure something's brightness, it'll just kind of bounce around nothing, not really much happening. And then if you have something change, it gets brighter, it will increase in brightness, obviously, and if it's a supernova, it'll continue increasing in brightness till it reaches some kind of maximum value. So this is the kind of generic shape that we would expect a supernova to have, or at least a core collapse supernova. A supernova that's run out of material and collapses in on itself. So this model that we'll try to use tries to replicate this shape by a few different parameters. And there are a few key points that we should think about before going on. One is to do with the star's properties. So a star is in this case, very well defined by, say, its radius. So from the center of the star to the edge, that's what we call the radius. And we might even put a little star next to that in some of the equations to remind us that it's the radius of the star. And then something else that's important is the mass of the star. So that's usually represented as an m. Now we usually measure these properties, radius and m, not in kilograms or meters like we're used to with, say, measuring ourselves, but with something that makes more sense in this framework. So in this framework, we're thinking more along the lines of the mass of the sun, which we represent as m dot, and the radius of the sun, which is r dot. So these funny symbols next to the m and r, these just mean the sun. So these values are something like 6. Geez, I'm forgetting now. Let me Google this so that I don't lead you astray. Now you can already see that I rely on Google an awful lot. Okay, so the sun is not, doesn't start with a 6, it's closer to starting with a 7. 0, 0, 0, 0, 0 kilometers. So, oops, that shouldn't go there. That's a 700,000 kilometer radius, which is pretty big, especially when you consider the Earth has about a 6,000 kilometer radius. And the mass of the sun is about, this one might take a while. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so the sun is 2 times 10 to the power of 30 kilograms. That's rather heavy and rather big. And as we're talking about stars, the sun is, we take kind of a standard case. Most stars in the universe are much smaller than the sun, but there are also a lot of very interesting stars that are much bigger than our sun. And in this case, the stars that blow up in a core collapse supernova are much bigger than our sun. So to save ourselves from writing too many zeros, it's much easier just to do things in terms of solar radius and solar mass. So we might say something like a big star is, 30 solar masses. And then that might correspond to, I'm not sure what exactly, but we might say, 200 solar radii. So these are the units that we generally talk about stars in, the solar mass and solar radius. But that's not all that we need. We need more than mass and radius, especially when we're talking about a star that's exploding. So these things are the things that we want to calculate. But we can't go there directly. We need to do some things along the way. And as we go along our way, we'll be calculating some different quantities, one being the photospheric radius. Now, this photospheric radius shouldn't be confused with the actual radius. The photospheric radius, the photospheric radius is the radius of the star as it's blowing up. So that's the radius of the supernova. See, the photosphere is, you could imagine, let's see, that's an okay circle, I guess. The photosphere is the last point on the star. So this is the photosphere. Beneath it would have different things, like for these big stars, it's mostly just a radiative zone. But deep down in the center, you'll have some very, very hot core, which has given up because it started making iron and has decided to blow up. So this photospheric radius will change over time. In fact, it'll get bigger over time because the supernova explodes and all of the material flies away from the star. There's also the temperature. So temperature is very important here because we're going to be saying that the light is emitted in what's called a black body distribution. So light will be emitted in the supernova in a whole bunch of different wavelengths. But what we're going to do to simplify it is to say, all right, the temperature, the photospheric temperature that we call T-phot, is what tells us how the light is distributed. So the light will have some kind of profile that looks like that, more or less. And this is called a black body curve. And the peak, this peak of the black body curve, is defined by the temperature of the object. So the hotter the object is, the more the peak shifts this way, where on the x-axis we have the wavelength of light, and on the y-axis we just have the intensity. So at different wavelengths we would have different intensities. So we're going to need to program something that gives us the black body radiation curve, and then we're going to need to work that in with how the temperature and the energy of, or the temperature and the radius of the supernova change over time. And both the temperature and radius depend on, or the photospheric temperature and radius depend on the original star's radius and the original star's mass. So with some of those things out of the way, let's go back to looking at some papers. So this paper here is using a model which was from all the way back in 2011. So it's way back when I was still in high school. So it's definitely an old paper now, whether we like it or not. And this one here is what we'll try to use. So this goes through and tries to characterize how the supernova behave. So the main equations from all of this paper are these ones here. Oops, that highlighted more than I wanted, but this R-phot, or R-pH of T, and this T-pH of T. So these different things give us the two important things that we just talked about, the photospheric radius with respect to time, and the photospheric temperature with respect to time. So there's a lot of stuff inside of these equations that perhaps we should unpack before going on. And to do that, let's scribble some things down and see what it looks like. So we talked about the R photospheric radius is a function of T. That just means that as time progresses, this photospheric radius will change. And this is equal to a whole mess of stuff. So if you run through the calculations like the authors of this paper did and do it all correctly, you'll get 3.3 times 10 to the power of 14. And that just kind of sits out the front. So that's kind of the default radius, photospheric radius of this thing. Then you have this other strange quantity, F rho, which we'll talk about in a bit. And that has a strange power. You're probably used to or have seen things being squared. So a number times itself is squaring an object. Or you can represent that as, say, 2 times 2. That's also equivalent to 2 squared. But also, say, the square root of 4, you could also represent that as 4 to the power of 0.5. So since we have in this F rho, we have a power negative 0.062. So it's like some weird square root you can imagine it as. But anyway, let's get rid of let's get rid of these things. So you'll see lots of strange powers here, and that's just the way that these things work out. But then we have this other expression, E51, 0.41. Now you also see a lot of these things. In this case, it's E51, and what that means is it's the energy, or it contains within it 10 to the 51 energy units. In this case, there's some weird thing called an erg. So within this 51, you can imagine it being divided by 10 to the power of 51. And that's the case with all of these numbers that have, or all of these letters that have a small number after them. That's just the normalization factor, we call it. We have a strange little k, which is normalized to 0.034, and it has this weird, this weird power again. And then down here we have m divided by m sun, if you remember that from before, to the power of 0.331. So since we're going to be working, or trying to work in terms of solar masses to begin with, we don't need to do this normalization by the sun's mass. Instead, let's just call this m. Okay, and then the last term here is T sub 5, 0.81. So this thing here is kind of the most important thing. Maybe I should use a different color. This thing here tells us how the radius changes with respect to time. So this is kind of the most important thing as far as this equation is concerned. So the sub 5 means it's 10 to the power of 5 seconds it's being normalized by, and again it's got a weird power, 0.81. So that's most of the important stuff there. So it's, really speaking, kind of a simple equation, and it's especially when you think that we're trying to use this fairly simple equation to tell us how a star blows up. It seems perhaps a little too easy to do that, but it is good enough. And there's also this next equation, T phot, which also depends on time, and it also has some weird things. So it's 1.6 F rho minus 0.037 E to the power of 0.02751, radius of our supernova, or our star before it blew up, to the power of 1/4, and that's normalized again. This time it's 10 to the power of 13 centimeters. So I did say that we like to use units of solar mass and radius. That's true, but in some cases it's easier but also confusing to do things in terms of centimeters. So in the case of stars, someone at some point decided that a good measurement was centimeters. And it's kind of built into the system, so it's hard to change at the moment. Then we have mass again to the power of 0.054, and the strange little k, 0.34 to the power of 0.28. And finally we have the time condition, so again normalized to 10 to the power of 5, 0.45. So those are kind of the two major equations that we'll be wanting to deal with. Now this little kappa, this strange little K symbol, this one here, that is a measure of the opacity. So the opacity is kind of complicated, but also pretty easy if you don't think about it too much. So something that is completely transparent, like say an imaginary cube, light will travel straight through it and not notice any difference. The same amount of light you put in is the same amount of light you get out. Nice and simple. But if something is completely opaque, so there's no way any light can get through it, the light will come along and just hit the object and not proceed any further. So the opacity is just kind of a measure of how far between these two extremes are you. Will everything pass through, or will nothing pass through? So these are what we mean when we talk about opacity. And for a supernova, light definitely escapes them, so we know that it's not this case. So it's generally not that. It's somewhere sitting in this middle ground is where the opacity of a supernova lies. And it may indeed change with time, but this simple model doesn't really take that into account, because that would make things a lot more challenging. And then this final term that we've also jumped over is this F rho. Rho being the strange P-looking thing from the Greek alphabet. And if we look through the paper some more and go up, we see that F rho is this thing here, where it's kind of a ratio of the densities. So it's 3 divided by 4 pi, rho 1 divided by rho star. Not sure at this point what rho 1 is or what rho star is. We can set rho star to be a random parameter that we fit while we do our fitting later on, or we can just say that it's, we can say that this is more or less equal to 3/4 pi rho star, where rho star is just some parameter. But anyway, that doesn't matter so much for now. What is probably more interesting to start to get going, now that we know the main equations that we'll be dealing with, those ones that we wrote down there, let's try and do some programming. So let me find my terminal. So this thing here, let me So pretty much everything I do is in a language called Python. And Python is a pretty straightforward language, so it's not too hard to get into. And this thing that you see now is called Jupyter Notebook. So this is the thing that I often use to do my programming, because it just makes things nice and simple to calculate and do work. Then later on I might put it in a more rigorous thing, like a file or something. But anyway, while we get into some coding, perhaps let's put on a bit of music to hopefully make things a little more entertaining. And remember, you can ask questions at any point, and we can get distracted as much or as little as you'd want. Also, let me know if anything seems wrong with the stream, or the music is too loud or anything like that. So anyway, let's get into how this code works. So in the beginning, every Python script, you need to do the same thing over and over. You need to import all of the different things that you're planning on using. In this case, the main things that we're planning on using are NumPy. So that's this first one. Now this does all of the mathematics that we might be interested in. Next we have this thing here, matplotlib.pyplot, and that is the plotting side of Python. So later on we'll want to check what we've done, and matplotlib is the way to do it. And this is a very useful piece of code, but also oftentimes a very painful piece of code. So, you know, things are good and bad. Then the last two things we have is from a package called AstroPy, which is developed by astronomers to make doing astronomy things a little easier. So we have this constant thing. So we'll be dealing with a few fundamental constants, like the speed of light, Planck's constant, and the Stefan-Boltzmann constant, to name a few. And these are better to just use the built-in values instead of trying to find them again. You may have the wrong units or something like that. And speaking of units, the last thing we have is super useful for doing this kind of stuff, AstroPy units. So this thing will allow us to give physical units to numbers, and it'll make sure what we're doing is correct. So for example, we have, say, an equation that we have conflicting units on. We're expecting to have temperature in terms of Kelvin, perhaps, but instead we give it in terms of Celsius. While both are valid temperature measurements, only one of them will give us the right answer. So let's get into doing that. So the first thing that we need to do is put in those equations that we had before. And I'm going to be putting these in terms of functions in Python. And to write a function in Python, you just do this, def, the name of the function. So we'll start off with, what was it called? fp, we'll call that function. And this takes some kind of input, say p from earlier, and what it gives us is 3 divided by 4 times numpy pi times 1 over p. So that'll do for now. And then to get this output, we just say return fp. So then if we were to want to run this thing, we'd say fp of 1, and then that would give us an output, which in this case would just be 3 divided by 4 pi. So that's in general how functions work in Python. So let's put in the more complicated ones. So the photospheric radius. Now what did the photospheric radius depend on? It depended on a whole lot of things. In it we had things like the energy of the supernova, so that's something that we'll be interested in fitting. We had the mass of the supernova, or the star that blew up. We probably also want the radius in there, and we want time in there. And for this we'll just, we should probably also put kappa in there as well. Let's just call it k for simplicity. Okay, so our font is equal to 3.3 times, we can just do a shortcut, e to the 14 times, let's quickly do this, fp is equal to fp of, we'll just say 1 for now. I have a feeling that I've missed something. Oh, this is very bad coding. Don't do that. So the problem here, which I should have realized, is that I've called my function by the same name as the variable inside it, and that's pretty bad. So let's call this f-row. That way we won't have that conflict. I think this is supposed to have a radius in it, so we'll look at that in a bit to make sure that's right. So fp to the power of minus 0.062 So these double stars here mean to the power of, and a single star just means multiplied. Multiplied by E. Okay. 3 divided by mass to the power of 0.054. So while I'm doing this boring coding stuff, if you have questions, please do ask. Thanks Linux Dog. Hopefully this proves to be educational in some capacity, if nothing more than seeing how I spend my time. And see how many typos I make, because let me assure you, there are a lot of typos. In fact, this is from the temperature equation. That should be 0.31 multiplied by T to the power of minus 0.81. Okay, and we just say return our FOT. But let's make sure we're doing things right. So we do u dot centimeters. So what this will do is it will do all of this calculation, and then once it's calculated the value, it'll multiply this FOT stuff by a unit, in this case by centimeters. And then after it does all of that, it will return to us the photospheric radius calculated in units of centimeters, which is what we want. So the next thing we want is def t font. And this is pretty much using the exact same stuff we had before, so let's steal some code from there. So let me do the same kind of thing. We'll steal this again because it also depends on that. And then let's put in by R of 4. Cool. Divide all of that by our mass to the power of 0.054. And multiply that by K to the power of 0.28. Lots and lots of powers, and really strange powers. But if you go through the math, this is how it ends up working out. So, math can be quite strange at times. So in this case, for the radius, it had a positive power, which means that the photospheric radius increases with time, but for temperature, it has a negative power associated with time. So that just tells us that the temperature decreases over time, and that's what you would expect to happen. So as the supernova expands, it cools down. So that makes some sense at least. Okay, so we have that, and the unit we want here is U dot Kelvin. Return T-font. Okay, so let us see if these functions give us errors. Let's just feed it all ones here. We don't really care so much. Okay, so it works. It's a very low temperature, which isn't entirely surprising because we've given it a radius of just 1 times 10 to the power of 13 centimeters, which is pretty small. A mass of 1 solar mass, and an energy of 1 standard exploding star. So this is okay. The main thing we were looking for there was that it didn't give us errors. So let's see what RFOT, does this work? Good. You can see that gives us Kelvin for temperature and centimeters for radius. So far this looks alright. Now that we have the radius and temperature, we should check that I had the right thing. Let me check. Okay, so I did have a mistake. That's fine. Mistakes are always happen. It's just gotta make sure that you try and catch them. So let me see. So we can change this to be actually, let's say 1 divided by P bar. P bar. Okay. Where P bar depends on the mass of your exploding star and the radius of your exploding star. So this is just the density of your star. So that's good. So we'll change this to be a function of mass and radius of the star. So we'll change these functions to be mass and radius as well. Okay. That should be fine. So now that we have the temperature of the photosphere at any given time, the main thing we want to do is try and see how the black body distribution will change. So the temperature is only useful so far as it tells us how the black body curve looks like. So let me find the Wikipedia page on black body radiation. I haven't bothered to remember what it actually is. What is it called? Or we could call it Planck's law, which is what Wikipedia prefers to call it. So let's quickly look at some Wikipedia stuff. So this is essentially what we're interested in. So along the x-axis is wavelength. So that's just the point in light which energy is emitted. And the y-axis is just the amount of light. Now the units on the y-axis are pretty important, and one to take note of is this SR to the power of -1, and that's just the solid angle, which we'll talk about in a bit. But as you can see, the higher your temperature is, the more the peak of the black body distribution shifts towards the shorter wavelengths, or towards ultraviolet light, and in fact the more energy it outputs. So for a supernova, you'd want it to be very hot for it to be nice and bright, or very large, because that plays into this stuff on the side here. So that's kind of what we're aiming for now. Let's find the equation. So this is the equation that we'll be using in terms of wavelength, space instead of frequency. Both are pretty much equivalent to each other, just the units that it spits out at the end. So in this case, B is the energy distribution, or the intensity, and all of this stuff is the stuff that we want to calculate. So let me pull this back away. Let's write a function for the black body. Now this, we only want it to take temperature for now, because maybe we'll also want to feed it wavelength later on, but for now that will do. So inside of this equation there are going to be a few fundamental constants, and we can use the const to do that. Const.c is the speed of light, units of meters and seconds. const dot h is Planck's constant in terms of joules and seconds, so energy and time. And what is it? Volts. I always forget this one. kb. There we go. This is the Boltzmann constant in terms of joules and Kelvin, so temperature and energy. So all of these fundamental constants we'll just use taking from the constant package that we imported earlier. Hey Sausage Jockey, thanks for joining in. Yeah, the removing the moon is something that's pretty fun to think about. So I enjoyed making that video. Next part, could you please remove the mic? There's no output on the right side, only music with no voice. Alright, that's very peculiar. I don't know how to fix that, to be honest. Yeah, sorry about that. Quite bizarre. I'm afraid that this might just be mono for this stream, but if we do future streams, I'll certainly try my best to fix it. So sorry about that. Clearly not the best at streaming. First time giving it a go. Yeah, and Sausage Jockey, we will try and science all we can out of this. So let's go back now, and I'll try and put in this equation. So B is equal to 2 times const dot h times const dot c squared divided by, maybe we should put a lambda in there. We'll call it lam. And lam to the power of 5. So again, we've got some more reasonable powers this time, but still pretty strange ones. Okay, so this is now mp dot, 1 divided by, let's put this out here actually. 1 divided by mp dot x of, now I've got to make sure I get this right because it's a pretty nasty const dot kb times lam divided by, already messed that up. Okay, let's just do the bottom part first. Times temp, and that is all dividing const dot h times const dot c. Okay, so that should be good, and then we subtract 1 from that, and that gives us our black body distribution. Now the thing to be careful of here is we gotta try and make sure the units balance. So in physics, a really important thing, especially when you're doing theoretical physics, is to make sure units balance. So let me take a slight detour and talk about balancing units. So let's go back over to my scribble zone, and we have that should be a capital T 2hc squared divided by 5 hc over kbt minus 1. Okay, so all of these quantities have units. I'll circle each one that has a unit. So this has a unit, this has a unit, this has a unit. These both have units, this. So pretty much everything in this equation has a unit associated with it. And because this thing as well has some kind of unit, all of these things need to be balanced in the right way around. So a good example for this, we won't go through everything because that would be, I'll make mistakes and then we'll get confused. Let's just look at this one, because this is the most self-contained. So we have e to the power of this stuff. So an exponential cannot have units in it. So if you had units in this, then you would end up with an e to the power of, say, centimeters or something like that. And how do you deal with that? You have a very non-standard unit, and what does e to the power of centimeters even mean? It just doesn't make sense. So when you have these functions, you need to have these units. They all need to cancel. So all of this stuff here, all of this, oh, that turned out not so great. Anyway, all of this stuff up here needs to cancel in terms of units. So this may be boring, but it is important, and something that, if you want to do physics, is always good to learn. So we'll put square brackets around it, and we say that we're talking about units now. So Planck's constant has units of, I cannot remember. So let's go back here, const.h, joule seconds. So in SI units, it's joules multiplied by seconds, and then the speed of light is in terms of centimeters, or sorry, I'm getting my unit conventions confused, meters per second. And this is being divided by a wavelength, which is in terms of meters, Boltzmann constant, which was joules per Kelvin, and a temperature, which is in terms of Kelvin. So Sausage Jockey asked, what was the deciding factor for your career choice, if you don't mind me asking? Yeah, so that's a good question, and one I often get asked because, you know, it's always good to see how people that ended up doing this kind of thing thought about things, for your own kind of guiding. I asked a lot of people that question as I was going along as well. And I'm afraid I don't have a really good answer for this, other than I was generally pretty interested in space-related things. All along, more generally, how the world and the universe worked. So when I was in school, I really liked reading about science stuff, especially theoretical physics, and that ended up leading me to where I am at the moment, just generally wanting to learn more about the universe. Then as things go, I found I originally wanted to do theoretical physics, but thought in the end it didn't seem too interesting to me, and I didn't really have the mental capacity to do it either. So I ended up going into astronomy, and for me, exploding stars was a pretty interesting aspect of astronomy, so that's where I am at the moment. So unfortunately not a good deciding factor there. It was just a general wanting to understand things, and in fact also just talk about things like I'm doing at the moment. I find teaching probably just as fun, if not in fact more enjoyable, than doing research itself. So hopefully that gives you some answer to the question, or at least filled in some time there. So anyway, back to the units. So we have here lots of different units, and remember they all need to cancel in the end if this is right. So we have a Kelvin multiplied by a Kelvin, or a 1 over Kelvin, so those two cancel. We have a joule being divided by a joule, so those two cancel. And we have a meter dividing by a meter, so those two cancel. And then we have a second being multiplied by an inverse second, or a 1 over second, so you could say a second divided by a second. So those cancel. So you can see that looking at the units of things is very helpful sometimes. It can tell you if you're right, and if you have the right units or the right variables in your expressions, or if you're just completely wrong on some aspect. So this is why we need to pay attention to the units of things, which is what we'll be trying to do now in the coding. Okay, so let's see how this will go. we will say that lamb has units of meters, because everything else is in SI units. So this should take care of itself. And then this should also take care of itself, because this is an SI. This is all in SI, and temperature should be in Kelvin, which is what we need for the Boltzmann constant. So, until we get our first error, this will be okay. So in this case, we'll return B. And B is just kind of the intensity of an emitting object, or an emitting sphere, or something like that. So this should hopefully work out. So for example, we do something like this, say T is equal to a generic T thought. Then if we try to do black body of T, comma, I don't know, say 200 meters. No, that's not right. Right, yeah, so this is when we get our first conflict of units in astronomy. So astronomy is all over the place in terms of units. And a lot of fields are. I often say they're steeped in their own filth, because they've been around for so long and so many different people have done different things at different points in history. You end up with different conventions and different things that make sense. So in this case, I was going to put in 2,000, and 2,000 meters is in the radio wavelength, which will get hardly any light from black body. But what I was intending to put in was the wavelength in terms of angstrom, which is 10 to the minus 10 meters. So maybe to preempt my own problems being an astronomer, we'll just say how do you do this? U dot angstrom. There we go. Okay, so this should give us something, as long as I give this the wavelength in terms of some kind of unit. This times U dot angstrom. Okay, well, that's right. Okay, so this is when we encounter the really first problem with units, and I should have remembered this happening. But before we get on to why this is so messed up, we have another question from the lovely sausage jockey. So the multiverse. Yeah, so the multiverse is an interesting one. It's also interesting because there are lots of different ways that you can construct an argument for a multiverse. It doesn't mean that either one of them is correct, it just means that there are different ways of approaching the problem. So the most common one is from quantum mechanics, where you have superpositions of particles, and observing a particle will break its superimposed state, so you'll get either one or the other as an output, and no in between. So often people think like, well, maybe both answers are true. Let's go back to scribbling space. So you have say something simple. Oops. Let's say we have, and oh man, this is all over the place. Let's say we have an electron, and this is in a superimposed state, so it is in what we call both a spin up and a spin down state. This notation probably isn't right, almost certainly isn't right. This is just what we'll use to represent it for now. And then some instrument comes along, or some particle, or something in the universe comes along. Say, I don't know, we'll just call it a box. So our electron passes through the box, and there's an interaction. An interaction happens in the box. Then out of the box comes an electron with just the spin up state. So the question is, well, where did the spin down state go? It was theoretically there a moment ago. Where is it now? Where's that information of the universe gone? Now a lot of people kind of find a solution to this problem by saying, well, both outcomes are true and both have happened. It's just that we occupy a universe. If we draw our box again, up, down, we occupy a universe where only the spin up option was available. So you could imagine this, instead of an interaction, this could also be called a universe splitter. And out of it comes an electron with spin up in one universe, and on the other universe, an electron with spin down. So both answers are probably true, but they just occupy different observable universes, which you have no chance of seeing or being on other side. So this is cuts to the heart of quantum mechanics, where it's so messed up and lots of probabilities and things like that. It's been a while since I've done it, so I probably shouldn't be answering too many questions on it. But anyway, the idea would be that at every point you have a universe split off. So you have, for every interaction of a particle in the universe, a new universe being created. So we've learnt a lot this year about exponential growth, for rather unfortunate reasons, but this would be a case of exponential growth, where you have something come along, splits into two, and then so you have one interaction in the universe, and then maybe another interaction in the universe, another interaction, so on and so forth. So you end up with this ever-branching tree of interactions where we're saying each one of them is a valid interaction or a valid outcome of the universe. Now this, there's no way at the moment to say that this isn't true. It just seems to me that there would be an awful lot of multiverse out there, but perhaps that's not a problem. Maybe that's just a problem for my human mind. So that's one way to get a multiverse. Another way, which is less perhaps quantum driven, or still is quantum driven, but more on a large scale and perhaps more realistic, is after the Big Bang. So we have Big Bang, the universe expands, and then things go on their merry way. So shortly after the Big Bang, there was a point in time, very, very shortly after the Big Bang, like 10 to the minus 60 seconds or something like that. Very, very shortly after the Big Bang, there was a period called inflation. And inflation meant that the universe expanded very, very rapidly, very quickly, and then kept going, and then started expanding again later on. So anyway, that's how inflation works. And it would be a quantum, or it's thought to be a quantum-driven process. So you could have like some random probability switch. A random probability switch that will make inflation happen in a place and turn it off, and you just have this big universe where just random pockets turn on inflation and turn off inflation. So each one of these little pockets would be a self-contained observable universe where you being inside one of these would have, at this point, as far as we know, no hope of interacting with another observable universe, say someone with many more legs than us. That interaction just wouldn't be possible. So, there are different ways of making an observable universe, or a multiverse rather. The problem is, at the moment, we just don't have any way of testing any of these hypotheses, because a universe is pretty much everything that you can observe. So, by our current understanding, there could be multiverses, but, will it matter much if we cannot interact with them? Who knows? Is a breakaway civilization like Elysium possible? I actually haven't seen Elysium, so I don't think Elysium. I will need to. I'll need to look on that movie and see later on. So let's, for now, after talking about some quantum physics and cosmology and things, let's return back to trying to get these units working. So it did exactly as we asked of it, as is always the case. Computers are incredibly stupid, but also incredibly smart. And more often than not, the stupid aspect of a computer comes from the person programming it, because they do exactly what they're told. In this case, the stupid part is our conventions. So we put in things, and what did we get out at the end? We got meters squared per joule, or times joule, and then we get per second, an angstrom to the power of 5. Well, that's not at all what we wanted, so an easier fix for that would be to just say 2 meters. Oops. Okay, I should have done that in the first place. Okay, so when we do that, when we change this angstrom to meters, second to meters to the power of 5, then this guy cancels out with this one, and we're just left with meters cubed. But this is where you need to know what you're doing, because it can be very easily to get led astray by simplifying things. So in this case, we have joules per second per meters cubed. But this meters cubed isn't actually meters cubed. It's actually joules per second multiplied by meters squared multiplied by meters. And you may wonder, well, what's the difference in this? Meters squared multiplied by meters, how's that different from meters cubed? Well, it's because these two things belong to different quantities. Meters squared belongs to an area, so the area of the emitting surface, whereas meters by itself, this one, belongs to the wavelength. Wavelength. There we go, that's close enough to spelling, right? So this is, this can be a point where you can get confused quite easily if you're not too careful. So we'll need to be a little bit careful here. And at the end of this, we'll say b dot 2. And what do we want? We want u dot j divided by u dot seconds times u dot meters squared times u dot meters. This will probably not do what I wanted it to do. No, it didn't. Okay, well, we'll deal with that later. So anyway, works, good. Except this 0 may be not what I wanted. Why is it giving me a 0? What's the temperature? Well, that probably doesn't help. The temperature at the moment says it's very small, and that is probably because the radius is very small. So let's change that. So let's say the radius that we're inputting is actually in terms of solar radii. So r times const dot r sun dot 2 centimeters divided by 1 E30. Okay, and in this case we don't really want 1 units floating around. down. So let's just say R is equal to R dot value. And let's do the same here. Okay, so now this should be a temperature in terms of, solar radii. That's marginally better, but also not so good. Let's see. What could be the problem? Most likely the problem is that this is just a very, very small star. So what order did I put these in? Yes, so let's make this a 10 solar mass star. Oh, yeah, so I should have realized this. So that we're saying this is pretty soon after the... maybe this isn't the solution. Oh dear, what have I done? Done. Well, let's ignore that problem for now. So there's another good way to code. Ignore problems until you can't ignore them anymore. By good way, I mean don't do it that way. Okay. So, we have our black body distribution. So, let's now do an equation. What is the deal with this? This is bothering me. This should work. The fact that it's not working has made me want to cheat a little. And pull out something I prepared earlier. Okay, there we go. Let's see if this one works. Oh, what have I done? Oh man, not even the thing I prepared earlier works, huh? Oh no. That is confusing. So, now we've really encountered the first bug of this. So now we get to have debugging fun. Says temperature and meters aren't convertible. So that means somewhere I'm trying to convert... What? Oh. So this is the problem with using code you used earlier. Alright. This goes there. Okay. Well, it's not 0, so we'll say that that's fixed. Yeah, so this was something I did earlier. Yeah, I wasn't paying enough attention. So the difference was the temperature was in terms of electron volts. So electron volts, yeah, so this is the problem with using different units. So to convert electron volts, which is an energy unit, to a temperature, we need to do this step here. Anyway, now we have a temperature. In this case, it's a really low temperature still, 210 Kelvin. That's below 0 degrees Celsius. Yeah, it is. It's well below. Okay. Well, this is a bad time for that supernova. It's very cold. So we'll say that this works now, even though there may be some other bugs lurking behind the scenes. Next step is to calculate the intensity of the light. So we have our temperature, our radius, and this black body distribution. The black body distribution tells us where the energy is spread and how much there is, but it doesn't tell us it doesn't tell us what the actual intensity of the light is. Instead, we need to do something. So let's call this calc intensity. And this has inputs of lam, temperature. Does it have temperature? It does indeed. Radius, and this magical thing called SR, which we'll call, which is the which we'll say is for most part is 4 pi. So this SR at the end is the steradian, so the solid angle of which the light is being emitted. So it's like in this case we're saying it's a sphere, so it's the angle of, the 3D angle of a sphere is where the light's being emitted. Oops, wrong way. Okay, so what we need for this intensity is it's the black body distribution, and that takes lam and t. And we also need our photospheric radius, which we've given in terms of r. Dot 2 meters, q dot meters. And then we also need to do our calculation. So the intensity of light is equal to the black body distribution multiplied by our area of a sphere, which is 4 pi times r squared, which is then multiplied by our, what is it multiplied by? Why am I drawing a blank? SR, that's what it is. Okay, so then we say return I. So in this case the units are going to be a bit of a mess. Let's test this. Calculate intensity. Lam we'll say is again 2000 angstrom is pretty small, so that's okay. 2000. We'll say this. Put this in more a red color. 5000. Okay, then the temperature. We'll say the temperature of the sun, 6000 Kelvin. 6,000 Kelvin times our radius, which we shall calculate now, worth just a whole lot of ones. Okay. What time is it? It is 5:30 in the evening for me, so I'm in the east coast of America. So it's still quite a bit of time left for me to be able to do things today, but 10:30 is getting pretty late. I certainly won't hold it against you if you decide sleeping is a good option to do. Okay. Alright, so this intensity is correct in terms of the units that we get out, but it's not correct in terms of the units that I want. Because we need this in a different format. And the format we need is in terms of wavelength space, or in frequency space rather. So lots of tricky things with astronomy and units. So I generally prefer working in wavelength space because that makes more sense to me. But if we want to do things with these models and the magnitude system, then we want to work in frequency space. So the difference between the two is pretty subtle. Let's go back to the scribble line. So in general, for some light, so we have some light, for a light particle, the frequency f times the wavelength is equal to the speed of light. So if you know the frequency of your particle, then you can then go ahead and calculate what the wavelength should be, and vice versa. But for this case, we have a distribution. We have something that looks a little bit like that. And you can't just do a one-to-one conversion, because that messes up the distribution. So you say you don't want to offend me, but you certainly have. Well, not entirely. Yeah, it does sound kind of Australian, my accent. But it's I'm from New Zealand, so I never really had what you would expect a normal New Zealand accent to sound like, I think. And then spending the last 3 years in Australia doing my PhD probably introduced a little bit of Australian into my accent. So you're not wrong, and not entirely offended, but never go calling a Kiwi an Australian. It's just bad form. But anyway, back to distribution. To get the distribution right, so at the moment we have it in terms of wavelength, and we want to take it to frequency. To do that, we need to do some calculus. So I always forget which way around this goes. So we have, say, c divided by lambda is equal to frequency. And we're going to be doing some... It's okay. Everyone makes the mistake at some point. It's like calling a Canadian an American. I'm told that the Canadians don't like being called Americans, especially at the moment. So if we do some calculus, we do d by d lambda of c divided by lambda is equal to d by d lambda of frequency, where this is just the derivative, or the change in a variable with respect to this variable, in this case lambda. So we won't go through the rules of calculus at the moment, but suffice to say, this side becomes minus c divided by lambda squared, and this side becomes df by d lambda. Now, because we're physicists and we don't need to take too much care with mathematics, we can do some pretty sketchy stuff. Mathematicians hate this. We can multiply. This isn't what you do, but it's effectively what you do. You end up multiplying both sides by d lambda. So then you get minus c divided by lambda squared is equal to d lambda equal to df. So if we have a distribution in terms of lambda, we can calculate that distribution in frequency space, just with this stuff out the front here. So this is, instead of just doing the one-to-one of, say, c equals, or rather, frequency equals c over lambda, it becomes frequency equals c over lambda squared. And this is a really important thing to do, and will mess up your calculations quite badly if you don't get that right. So let us do what all of that talking was trying to get to. And then there's also the fun thing of, I want to convert this to the units that I need now instead of SI units. And the units astronomers need are like the strange thing called ergs. I can't remember what it is. Let me see. Let's see. U.erg to U.joule. I think it's 10 to the minus 7 joules is a single erg. So it's a strange unit. More junk from history. U.erg. Divided by U dot meters, I believe. is equal to we want this this weird multiplicative thing at the front, so lambda squared. We want this in to u dot meters, lambda squared divided by const dot c, multiplied by our intensity, so that will put our intensity in units of frequency. But if we do this, let's see, what does it give us? U is not defined. That it isn't, it's only small u is defined. Okay, so what this gives us is in terms of erg, and that is not what we want. Our units have ended up cancelling in a way that we kind of alluded to before, and if you weren't prepared for it, would be quite confusing. So in this case, we had our intensity had units of ergs divided by meters times seconds, and then we went ahead and multiplied it by, what was it? It was lambda to the 5, I think. No, lambda squared divided by c from memory. Is that right? It is. Okay, so lambda, I shouldn't have written like that. We should write in terms of their units. So this has meters squared, this is meters per second. So if we do all of the calculations and cancellations, well, this cancels with that cancels with that, this cancels with that, so then we're left with erg. But the thing to remember, like we talked about before, not all units are the same. They can mean different quantities. So in this case, this stuff here, this is going to be changed. This is going to remain. And this is also going to remain. So what you end up with is what we want to have is it to be in units of per second per hertz, where a hertz is just 1 over a second. So again, it's this kind of thing where units can end up cancelling with each other. And we've lost our units of area because we've multiplied earlier by the emitting area. So this part here, this r squared, that will remove our area units for now. But we'll find them again shortly. So the way to fix this is to plug in our units that we want. So let's just say that we divide this by u dot seconds and divide it by u dot hertz. So then if we calculate again, good. We now have ergs per hertz per second, which is the units that we were after. Okay, so it looks like the intensity is working, or at least in the way that we want it. Now this is the amount of energy that you'll receive at each frequency for a given second if you collected all of the energy of the star. So let's return to the scribbling space. So here you have your star, a bit of an oval shaped star, and if you had like a net around your star, then you would collect all of the energy, and then you would get the intensity. But we don't collect all of the energy of the star, we collect only a fraction. Now it's even more oval than before. Not very good drawing. So you could imagine it as the further out you go from the star, the more the energy gets spread further and further out. So the energy density over the sky decreases. The total energy remains the same, but the energy density decreases because the radius of this one it's the radius in the initial state is much smaller than the radius in the final state. So if we have our star very far away from us, and we're sitting on Earth or in space, wherever, and we have our telescope set up. How do you draw a telescope? Something like this. There we go. Have our telescope set up. It will be intercepting some of the light at some distance away. And this distance is how we will get our area units back. So this is the this is just like, yeah, it's just the distance between us and the object. But we don't yeah, lots of different units. I won't bother going into all the different units. But anyway, that is the distance we have. So then let's make a new equation. Def. Say calc flux. So this flux is just the energy distribution over some space if you're a certain distance away. So we have an intensity and we have a distance. And we want to make sure that our distance is in terms of centimeters, which is also confusing. Why do we want to measure distance in terms of centimeters? More historical baggage in astronomy. Okay, so this is pretty easy. We just need to do flux is equal to I divided by 4 pi, the area of a sphere, surface area of a sphere, multiplied by the distance squared. And return the flux, not the glux, the flux, there we go. And that should give us the flux at any given point. Okay, so that is most of the equations that we need, all separated out. So each one of these will do their own individual thing. This one calculates the photospheric radius, this one the photospheric temperature, the blackbody distribution, the intensity, and the flux. So it's always good to keep things separate so you don't end up with one enormous thing that just overrides everything, becomes a nightmare to try and understand. So compartmentalizing things makes it a little bit easier. So let's perhaps cheat again and grab some code that was prepared earlier. This thing here. Okay. So this function here wraps up everything that we've done so far. So it takes the energy of the exploding star, the mass of the star, the radius of the star, some time interval, a distance away from us, and some opacity that we're just saying is 1. And then it divides the time by 10 to the power of 5, so we normalize it correctly for the equation. And then we give it some wavelength range, so this is going from 1,000 angstrom to 50,000 angstrom, so that's like the ultraviolet to the infrared, so that's a pretty big range. Then here we just have a for loop. There's probably smarter ways of doing this, but what will happen is that for each time value, it'll run around this loop and do this calculation, where it'll calculate the radius, the temperature, and store them in some array. And then it will also calculate our blackbody distribution, and then the intensity, and then the flux, and store that in some array. And then at the end it'll give us all of those things. So let's see how this works, and let's make an array of time. T is equal to the array of 1, maybe we should go 1 to 100 10 steps of 1 multiplied by 1e to the 5. Okay. Why did I like that? Ah, because that's wrong. Range is what we want. Okay. So let's put in our... what do we want to use? We want to use some energy. Mass, we'll say, is, I don't know, 20 times the mass of the sun. Radius of this thing would probably be at least, say, 200 times the mass of the sun. Time is t. Distance. That's a good question. What distance do we want? Let's do 10 u dot parsec, where a parsec is just another unit of measurement in astronomy. Okay. So, what does that do? It gives us an error. Calc intensity is not defined. Oh dear. We can fix that. Calc intensity. How did I spell that? Oh man, that's a bad spelling mistake. That kind of stuff happens often though. Calc flux should go here as well. Okay. So then it gives us this. So what this is it's an array. It should be an array. Oh. That's because it outputs flux, temp, and radius. Okay. So if we do flux.shape, that'll tell us the shape of this. So we have 100 time steps, and then we have 49,000 wavelength units. So, an awful lot of stuff going on there. Cool. So let's plot this. Plot flux. Let's take a guess where a good wavelength would be. Let's go a few thousand. Okay. So this isn't too bad. The units might not be right. I'll need to do some checking. But what we have here is generally what we want to see. So this is in terms of flux. Let me put some labels on this. Time. This is a second. I think I should. Actually, let's do this in terms of days. So time divided by 60 squared times 24 Ds. Okay, so this gives us the time and days of the supernova that explodes. So you can see that it gets brighter over time until it reaches its peak brightness, in this case around about 50 days or so for those random variables that we chose, and then it starts reducing in brightness. So this is, reasonably... Does this look okay? Well, we can look at the paper that did the fitting to the Kepler stuff. And it has the same kind of shape. In this case, it peaked at around 10 days. So maybe let's try reducing or increasing the radius to 490. What does that do? It gives us an error. What did I do? What have I done? Object is not callable. Huh. That one's confusing. Oh, I see. I see. I overwrote the function. Some bad coding. Okay, what does that give us? Ah, that's even worse. Maybe reduce the mass. Yeah, that's not ideally what I was wanting to see. So ideally, we would have wanted this to also agree that after 10 days, the peak should happen. But it seems like somewhere there's something going wrong, which is giving this a much longer time frame. What could that be? Question, and possibly a question that will take me a little while to find the answer to. A little while indeed. So maybe the thing to do now, instead of watching me debug this for a while, because that'll be tedious for me, so I'm sure that won't make for any kind of interesting ideas, or an interesting thing to watch, that's for sure. So let's give me a moment. Where am I looking? So, how about for the remaining ones that are sticking out to the end? Thanks for coming along. How about we? Oops. Sorry about that. So, for the ones that have stuck around to the end, I'll run away for a moment, and then when I come back, if you have any final questions, put them in the chat, and then we can have maybe a short discussion about these things. But I'll be back in a minute or two. Put any questions you have in the chat. Okay, I'm back. Sorry, ran away for a second there. So, does anyone have any questions? You know, anything at all is fine. If not, I'll continue doing my debugging. But please do ask questions if you have them. Can be on anything at all. Actually be there. There may not actually be a problem. It may just be the wavelength that shows was quite a bit different to the one that I was trying to compare to. So let's look at where do I define lambda here? So, where is lamb? Equal to value equal to 5,000. It's not 5,000 or 50. Okay. Went way too red. Ah, there we go. What do you know? There was no problem. That's what I get for randomly choosing something. So the problem there was that I was just plotting the wrong thing. The random wavelength I chose was actually, let's look. What was the random wavelength I chose? 10,000. Lamb of 10,000. Yeah, so that's 11,000 angstrom, which is pretty red, almost too red for this. And what this figure was looking at would be light around 5,000 angstrom. So we're about an order of magnitude out there. So this perhaps doesn't look so bad. It's not exactly on 10 days, but you know, it's close enough. Close enough for this, at least. Okay, so what is the next thing to do? We have a model that we say is correct for now, at least. So then, what good is this model? Well, this model is good if we want to try and fit it to data. So let me find where that data is. So I've got a mess of files. Actually, you can see all of the horrible structuring I do of my files. Okay, so I think it's in here. Now I want this one. Do I have It's probably one of these. No, I don't want that. Yeah, this is the file I want. So all of these are different data files. We have different sources of data on this one supernova. This one is from ground-based observatories. So there's I'm not sure which one. Here we go. There's the Zwicky Transient Factory or facility. I forget which way it goes. So that's ZTF. Then we have also Atlas, which is primarily an asteroid detecting satellite, or asteroid detecting telescope based on the Earth in Hawaii. That seems... Oh, and then we have GPC. And that's from the Pan-STARRS telescope, which is also based in Hawaii. I think Atlas is on the mountain Mauna Kea, but I can't remember for certain. I think Pan-STARRS is also there. And then one observation from Gaia, which is a space telescope. But anyway, we aren't worried too much about that. The data that we're most interested in is in this one here, which comes from TESS. And it looks like a mess, lots of numbers. So let's bring this data into what we can actually use. So let's call this TESS equals imperial text. Where was that saved? So let's do another figure and see. What this is. Actually, let me check the shape of this first. TESS. Okay. Here we go. So it doesn't look like much, really, perhaps. Okay. So this first part is kind of just the telescope doing its own thing and being pretty messy. But at the middle is where the supernova happens. So you can see quite clearly. If we zoom in here. The explosion occurs around about this point. And then it rises, and then there's some gaps in the data, which is pretty annoying. We didn't know that was going to happen, but it did. And then it continues rising slowly. So then the question becomes, how do you fit this model that we've got here to this data? And that is a very good question, and one that might take a little bit of working. So, we might as well get started. But if you have questions, of course, please do ask. Because this is... I don't need to do this now. We can just answer questions if that's more interesting. So... Let's optimize, minimize. Okay, so this function here that I just imported will help us in fitting things, so it's pretty useful. Next we need a function that will fit what we want. So let's call it def fit. So this will take a few different things. Yeah, I often listen to jazz. It's a nice calming way to code things. If you're stuck on the same bug for too long, then some nice calming music is definitely required. Because I mean, sometimes, like this, I probably shouldn't say this, but sometimes I've been stuck on a bug for days or maybe even a week, and then after checking everything, it always turns out to be something simple, something completely unsatisfying. Like if it's a really tricky thing, like the Python doing some strange bug, then once you've solved that problem, you feel some satisfaction in finding it. But if the error you've been stuck on for so long is like you mistyped something in one place or put in the wrong value for something, then that's a very unsatisfying thing to debug, and it's very, very annoying. But anyway, enough about the pains of coding. Let's try and make something that works here. So, what we're going to want to give this function is we need to give it the parameters, so let's call that param, and we need to give it our data that we want to fit, so we'll call that data. Easy. Now param will be kind of holding a whole bunch of different stuff, so it'll hold e, which will be param of 0, it'll hold the radius, which will be param of 1, it'll hold the mass, which will be param of 2, not kilograms, 2. What else do we need? And then something else that it's going to need is T explosion. That'll be param 3. There may be some more that we'll add on, but these are the ones for now that we want. So now the thing to do is, with these parameters, we would want to do this. We'd want to calculate the rise from it. We also want to give this a wavelength for now. This will need, we'll get to that in a bit perhaps. So this was the energy, this was the mass, this was the radius, and this is the time, which will be measured in days. Oh, and we'll also need to give this a distance. But we'll know the distance more or less, so we can just let's just put that in. Not dust, distant. Okay, so then we have a flux, and for now, let me see this view. Let's see, what is the central wavelength of TESS? This won't be so good, but it will be good enough. So for now, we'll say this is equal to 7,455. Okay. And that is in terms of U dot extreme. Okay. So that's the wavelength that we want to evaluate this at. So that's an important part, and this strictly isn't quite right. So let's go back to Scribbleland to explain why that isn't quite right. So we have our blackbody distribution, which will look something like this, and it will evolve over time. But the telescope doesn't see the entire spectrum, it only sees a fraction of the spectrum. If it's a a normal filter, which is pretty narrow, say is only this wide, then you can usually say the value at a particular wavelength, called the effective wavelength of the filter, is the flux that the filter receives. But for TESS, it has a really big filter. It goes something like this. And because the filter is so big, it means that saying that the effective wavelength, which would be somewhere around here, that's kind of pointless, because what you're really measuring is kind of the average from this entire range. So so the flux would need to be some kind of average over the range. But that's I have some code to do that, and it's kind of boring. So for now, at least, we'll just take the effective wavelength of TESS, which should give us something kind of close to reality, at least. Okay, so there we go. So then we want to do. We also need where our lambda is defined. So then we want to do some index value. I always call it ind. Lam is equal to wavelength. Okay. So then we want to take, say F is equal to flux of ind. So that's just saying find where the wavelength range is equal to the wavelength that we're interested in, and then only take the flux value that we calculated up here that is in the same place. So that should give us a close enough approximation to the flux that TESS will observe. Alright, so we have a flux. Next, we want to convert the time. So the time, all these things that need to go into it. We also need to time here. So call this TT, because that's some lazy coding. Divided by 60 squared. Times 24. So that will give us in terms of days. And then we want to add TEXP to it, so the explosion time. And then we need to do some kind of trickier stuff, perhaps. So what's a good way to explain this? Back to Scribbleland. So we have two light curves. We have the measured one, which kind of messy, and then goes up like that. And then we have our observed one, or our modeled one, which ideally will also just, at the moment, it just goes up like this. And we need to add, if we do plus TEXP, then this should go like that. But then there's all this stuff here in front of it that's missing. So what we need to do is kind of pad this model. We need to add all of this stuff in. And we also need to cut all of the stuff that goes too far, that our data doesn't cover. So let's try and do that now. And the way to do that is probably with terp. Oops. Terp. Okay, how does this work? I always forget. Okay. So, what we can do here, while we're defining all this stuff, let's do data time. So do data 0, data flux, so do data 1. So this is just selecting what parts of the data belong to what. Okay, so then we go. We want to say new, or say model flux. So to interp. Okay, data time tt, and then f. So this will probably break now that I think about it. How do you fill your values? So the problem here is that the interpolation won't like that it's going out of bounds. So instead, let's use a different one. Let's use terp only. Okay. So let's get rid of this. Terp. And I think we need to change this so that we get rid of time here. Finish that. Okay. Okay, so then we need to do bound 0 equals false. False. Not false. And then fill value equals 0. So that's just saying if it's outside of what our model calculates, just set it to 0. That way we shouldn't have too many problems. Okay, so then we want to do, residual is equal to data flux minus model flux. Let's take absolute value of that. So there's no negative numbers here. And then we want to do maths. So this will sum up all of the values and give us a number of how different the data is to the real thing. So let's go to Scribbleland and explain what that means. So here's our axes again. Here is our data. It goes up like this. So if we start off with our model here on some weird shape, and then did model minus observed, then it would look something weird. It would look maybe very negative down here, and then very positive up here. So that's not close to being right. That's very wrong. But if you were to just add up all of these numbers together, then you might find that they would come out to be something kind of, if you added them all together, summed it all up, it might come out close to being 0. In which case, the code would think, yeah, that's a good fit, let's go with that. But really, it's a really bad fit. So that's why we do the absolute value, which means that instead of this shape, it would give you a shape that looks like this, where the sum would be much, much bigger than 0. Very big. Which is what we want. That tells it it's done a very bad job. It needs to find better choices for the parameters. Okay, then we just say return res. Now, will this work? That is the question. So we need to say x naught. These are just our input values. They can be 1, 100, let's say 20. The explosion, that's going to be pretty high. Let's say 5, 8, 9, 30. That'll put it somewhere. Let's say 5, 8, 9, 40. So that'll put it somewhere around about here, which is pretty close. What else do we need? A distance. Let me search what this supernova is. What did I call it? FQV. How far away is this supernova? Pretty far. Let's look on this thing. This is the Open Supernova Catalog. So every bit of information you would want about any supernova should be on here. 2020 FQV. There it is. Okay. Where does it say its distance? Distance. Okay, this one, DL, in terms of megaparsec. So 33.481 megaparsec. So if we go back here, 33.481 times dot megaparsec. Okay. Now it's time to get some errors. Minimize. So this takes function, which is fit that. Then it takes our initial guess at parameters, which is that. And then it takes extra information, which in this case, oh, that doesn't go there. This case is our data, TESS, our distance, which we call dist, and that should do. What else is this missing? Energy, radius, mass, explosion time. Okay. So, in principle, this should run and give us some output, but I suspect it'll give us errors. That one's a pretty easy one to fix. Args. This one may not be so easy. What? Megaparsec. I see. That's not what I want. So, where do I define that? Probably calc dist. Where does that happen, I wonder? Let's just search for that new.parsec. Just drop this. New error. What's this one? Boolean index did not match the index array. Okay, that's an easy fix as well. Good, just easy things so far. So this one, I just need to do this. Yep, sure. See if that works. What's the problem now? X and Y must be equal lengths. This is probably also an easy fix. I suspect I haven't done this right. Yeah, let's see if this works. Export it. Quite right. So, what I forgot to do is evaluate the model at our data time. And it seems to be running, though it will give us junk. Did it successfully run? Apparently. But it also didn't do anything. Oh, that's not an ideal sign. Yeah, so fitting stuff is always goes like this. Huh. So let's try taking the log of this and see if that improves our chances. No, it doesn't. So what's happening here is that the incremental changes it makes to the parameters aren't actually changing the fit that much, or the model that much. So then when it does the difference, it gets pretty much the same result, which means that it doesn't really go anywhere. So this is going to be a problem that will require me to just kind of sit down and fix, which I don't think at all will be that interesting to see. But in theory, this is how it will run, and maybe in the future we can do another one of these streams once I've worked out the bugs and finish up modeling some supernova. So does anyone have any final questions? If not, it's been fun for me at least. I hope that you've learned something sticking around. So if you have any questions or final comments, just chuck them in the chat. So just to recap, what did we do? Well, whoops. What did we do? Well, we set up all the equations. That's an important thing to do. We made a function to fit to the data. Oops. To the data. I should have split these points up a little more. It doesn't look like we've done too much. But these things can take quite a bit of time to set up and get right, because mistakes here and there can be pretty annoying. So, I'm glad Harvey liked seeing the supernova light curves. Maybe in the future he'll be able to see some fit light curves that actually make some sense. But I think this is probably a good place to stop, because the next part will be lots of me trying to work out why this fitting doesn't quite work, and maybe using a different approach to fitting. So, for those of you that stopped by and have stuck around, thank you so much for watching. I hope you have learned something, or at least saw a little bit of what it's like for an astronomer to do some work. This was a little bit slower than what I usually work, of course, stopping to explain things, but I'd be happy to do this kind of thing again if people are interested to see more science in action, ask questions as we go, of course. But yeah, for now, thank you all for watching, and I'll have a new video on something science related in the near future, which will just require me to think a little bit about some things. But there's lots of really cool stuff happening in science, as there always is, and lots of really cool questions that we can answer. So anyway, thank you very much for watching. Let me know if you want to see another stream in the future, and of course what time works best for you. Trying to see what time works for many different time zones is pretty tricky, of course, but if as long as there's someone here who finds it interesting, then I'm not just talking to myself. So, once again, thanks for watching, and I'll see you all in the next video.